This is Maths 2017. I'll do the first question, just the first 10 multiple choices. Let's get straight into it. We're looking for two distinct stationary points. So differentiate, nice and straightforward. Stationary points are when the derivative is 0. Again, easy. Now b squared minus 4ac needs to be greater than 0 in this quadratic here because we want two distinct real stationary points. So okay, that's a, that's b, and that's c. I can just be lazy and square 2k rather than minus 2k because they both square to the same thing. Just make sure you do square it though to 4k squared. Divide everything by 4, and now this is a quadratic. I mean, actually, I think what I did was move the 12 over and then square root. 12 is 4 times 3, so the root is 2 times root 3. So critical values at plus or minus 2 root 3. Now, if you draw this quadratic here, y-intercept of minus 12, critical value is 2 root 3 minus 2 root 3. You want to be greater than 0. You want the quadratic, you want to be above the x-axis. You want to be more this way than 2 root 3, so bigger than 2 root 3, and less than minus 2 root 3. And we'll get those two answers there. Good. Number B. So this looks like a quadratic, a hidden quadratic, power 4, power 2. So just write the equivalent quadratic. Here it is, 9y squared minus 12y plus 7. And just complete the square on this. So take out the 9 from the first two times is how I like to do it. Halve this number for 2/3, take away the square for 4/9. Put the 9 back into the two terms that you've taken it out of. And then tidy up, and we get a minimum value of 3. But of course, that's not going to change if you just change out y for cos squared, right? Now if I just write this as cos squared all squared, and just replace this y for a cos squared, and replace all these y's with cos, all the y squareds with cos squares, and therefore the y's with coses, the minimum value is still going to be 3, right? You're just eventually going to end up here, and the minimum value is still 3. So it doesn't make a difference, and we just have the answer there. C, okay, so just play around. When you've got a thing like this, what you're hoping for is some kind of repetition. Again, I only know that because I've done questions like this before. But maybe you didn't know that when you went into the question. Just try stuff. Just plug in some numbers and see what happens. Like you don't have any other plan. So okay, n is 1 gives you a2 equals a1 over a0. And now a2 is 6, a1 is 2. So a0 is the third. Now that's going backwards, so we want to go forwards here. So okay, that's a bit of a mistake. So in this case, let's just set n as 2 instead, and then we get a2 is a1, sorry, a3 is a2 over a1. But we know a2 and we know a1, so we can plug those and we get a3 as 3. Then do it again. When n is 3, we get a4 equals a3 over a2, which we now know both of those things, 3 and 2. So that's 3 over 6, which makes a half. And the next one, so we get a5 is a4 over a3. You can see where this is going. You just take the previous answer you got and divide it by the one before that. So this is going to be a half divided by 3, which is a sixth. And the next one is going to be a sixth divided by a half. Divide by a half is the same as times by 2, so that's going to get you back to a third. And then a third divided by a sixth, that's the same as timesing by 6. So that's going to take you to 2. And then 2 divided by a third, same as times by 3, gets you to 6. And that's quite interesting. And then finally 6 divided by 2 is 3. That's quite interesting because now we're repeating what we had before. A third to 2 to 6, a third to 2 to 6, then to 3, which is what we went to last time. And so now it's just repeating. So we've just got a bunch of repeats going, well, starting at A1 maybe. 2, 6, 3, half, sixth, third, 2, 6, 3, half, sixth, third, and so on. So that's quite cool. And let's just pick, the way to do this is just pick a value that you want. I'm just going to pick 2. And say A1 is 2, A7 is 2, the next one would be A13 is 2, just by moving up another 6, and then A19, I guess, and so on. And all I need to ask is 2017 in this sequence? Now this sequence is 6n, because it goes up 6, minus 5. Is 2017 in there? Now if it is, that's great, and I'll just solve it. I get a whole number, which is good. Which means it is in the sequence, which means A2017 is also 2. Now, if it weren't in the sequence, that's fine. I would just need to go back to primary school and write whatever remainder was left. And if it was like remainder 2, I would just go 2 forward from whichever value, from one of the 2's. So if this was 337 remainder 2, I would say, okay, it's 2 and another 2 to get to 3. Or this remainder 1, I would jump another 1 forward and get to 6. But since there's no remainder, it's one of the 2's, just like all these are, and the answer is 2. So yeah, kind of interesting. You see that question, or that type of question, quite a lot. This one here, so this is a reflection in the x-axis and then in the y-axis. Just take this kind of C shape here, reflect it in the y-axis to put it here, and then reflect it in the x-axis to put it up here. And the only two graphs that do that are these two. And now it's clearly not this one here, because like when you reflect this and reflect it again, the shape of the graph is going to stay the same, right? It's going to have this asymptote here of being approached upwards this side, downwards this side, just like this one does, not like this. So it's definitely going to be this one here. Just do this in the brain dead way. You can rearrange this for b equals 20 minus a, shove it in there and then differentiate, or you can just pick two values, work out what they make, then try and make it bigger, which you can do, and then try and make it bigger again, which it doesn't work. So what you figure out is you have to go downwards, not upwards. So 14 and 6 maybe, which makes it bigger. Cool. Do it again. You make this. I mean, I was just doing a lot of column multiplication. It doesn't take me long. I teach a lot of year 7. So okay, try one more just to make sure you found the optimum, and this is the optimum. That's there. Again, there are more intelligent ways, but for me at least, that was the quickest way of doing it. This one's quite interesting. So you're defining each coordinate as cos x sin x, and you want sin x to be bigger than cos x. So in other words, you want the y coordinate to be bigger than the x coordinate. So okay, the x coordinate tells you how far to go across, the y coordinate how far to go up. You want to go up by more than how far you go across. That means you can't be here because you're clearly going across by more. You need to be above this line. Like, you need to be in this section, because this line defines where it means to go across by less than you go up. Right? Everything above the line that we usually call y equals x. So above it is y bigger than x, y coordinate bigger than x coordinate. So we want to be above this line. So we immediately eliminate a and e from contention here, just by this. Now thinking about tan is sine over cos. Now when cos is very small, so in other words, like let's think about this point here, where cos, the distance across, is very small. If cos is very small, tan is very big, because when you divide by a very small number, you get a bigger one. And so we can't be in here, right? Because tan just blows up when cos becomes very small. So we can't be in B. And now in D, the problem with D is, down here, both cos and sine are negative, like because you're in the negative x and negative y quadrant. But two negatives divided make a positive. So tan can't be less than these two things down here, because those two are negative and this one is positive down here. So that can't be the case either, and we have the answer of C by process of elimination. Good. Now this is the question that really messed me up on the paper. I had to do a lot of work for this. So you'll bear with me while I try to explain it. Obviously the first thing I do is draw this. We've got a circle radius 2, interesting. And we've got this, which is apparently a line, which is quite cool. What I first thought to do was just try some values. Put theta as pi in. Cos of pi is -1, sine of pi is 0, so we get this, which turns into this, which I can put down there. And now what this is saying is, let A of theta denote the area of the larger region. So there are two regions here, this one down here and this one here. A of theta is the larger one. And it's asking us how many times does A theta reach a maximum. So in other words, what I should probably do is try a couple more values of theta and just see whether or not it always stays in the same place, because that will tell me this one, or other. I don't really know what I'm doing, as you can tell. So let's just try some more values. Theta is 0 is a super obvious one to do. Cos of theta is 1, sorry, cos of 0 is 1, sine of 0 is 0, so that is also nice and easy for us to do. We get this, which is interesting because that's the same line. And also theta is 2 pi would give us the same, because cos of 2 pi is 1 again, and sine of 2 pi is 0 again. So okay, there's a bunch of values that just give us this exact picture. What about if we try to make cos 0 instead? So pi over 2. So now this is 0 and this is 1. So we get this, which is this line here. X equals -1, I believe, yeah. This line here. So okay, well that's, by symmetry, that's just going to be the same area. A of theta is going to be this bit here. And by symmetry, that's going to have the same size. So there's like 4 values that give us the same size here. But also there's another value, right? Because you could just go to 3 pi over 2, and that would also give you 0 and cos, and -1 is sine, but that would rearrange the same thing, or at least put the line in a similar place, and we have this anyway. So okay, that's 5 values that give us this area. But surely, so which means maybe the answer is that this is constant, and it's all values of theta. But then the next most obvious theta to try is pi over 4. Because I know pi over 4 gives you 1 over root 2 for both of these things, but that's quite cool because they just cancel straight away, and you don't have to mess around with them. You get this, you can rearrange it for this. So this is a line. Now remember, the radius of the circle is 2, so that y-intercept is up here. And likewise, this intercept down there is there, and we get this line here. I'm drawing this sine graph for some reason. Oh, I'm drawing the sine graph because, just to show that pi pi over 4 is not the only value for which you get sine and cos the same as 1 over root 2. And I know I've done this in degrees, which is dumb, but it was just because I copied this from something else, and I couldn't be bothered to find a radians one. So sine and cos are the same at 1 over root 2. Sorry, at pi over 4, which is 45 degrees, at 1 over root 2. But also at 225, so pi over 4 beyond pi, which is 5 pi over 4. They're also the same down here at minus 1 over root 2, which doesn't matter, they would both still cancel, so you get exactly the same thing for this. So there are two values that give you this line here. But looking at this line, it looks like it might be better. This area here looks like it might be smaller than this area here. And if it is, then that renders all of this stuff pointless, because I found a thing where a of theta is bigger. I found another value, and there are two values that take that. Okay, so now I'm edging towards this answer, two values that give me this line here. I've got a few things to figure out here. Firstly, I'm quite interested in the fact that all of these lines go through this point, which is clearly minus 1, 1, because this intersects with this at minus 1, 1. So firstly, I'm just going to quickly show that all of these lines here, whatever value of theta, always go through this point here. And the way that I did that was dividing by cos theta, and then writing it like this, just by adding 1. And now, if you draw your graph weirdly like this, with axis x plus 1 and y, this is just the line y equals mx plus c, where the x is just an x plus 1. And so this, regardless of theta, all changing theta does is change the gradient. The y-intercept is always 0, 1. And all changing theta does just changes the gradient around this point 0, 1, because it's just part of the gradient. But of course, all this kind of graph is, with normal axes of x and y, is just this one shifted back one place. And so all of these lines are just rotating around minus 1, 1. Right? Changing theta is just rotating these lines around this point here. Okay, so that's quite cool. So now that we've got that idea, we need to figure out, is this line here, which looks like it could be the best to make a of theta the biggest, is it actually the best? And there's a few things I want to talk about. Firstly, I'll say this coordinate here is root 3, 1, because it's got a y coordinate of 1, put it into here, and you get x as root 3, of course, to make that 4. And now this is, of course, minus root 3, 1, for the same reason you just square it to get plus or minus root 3. So this distance is 2 root 3 across there. Now this distance is 2, and this distance is 2. So by Pythagoras, 2 squared plus 2 squared is 8. Root 8 is this distance here, which is 2 root 2. So this distance is 2 root 3, this distance is 2 root 2, which means by symmetry, this area up here must be smaller than this one here. Because like if you, this distance is 2 root 3 right now, if you move it up and make this distance smaller, so 2 root 2, this area has decreased, right? And then you just spin the circle around and you get this area here. So this area, caused by this diagonal line, is definitely better than the two areas caused by the straight lines. So right now I'm leaning towards saying this area is the best, right, caused by this diagonal line, and there are two values that do that, pi over 4 and 5 pi over 4. Now, how do I very quickly prove it's the best? And maybe in the actual map paper you wouldn't want to do this. You just say, okay, this feels right, let's underline it. But if you just kind of tilt this line ever so slightly, just imagine you're tilting it a very small amount around this way clockwise. It's tempting to say that the area hasn't changed, but when you draw a line of symmetry in, it becomes clear that it has. Because if you imagine the area that the black line is creating down here being split into two, into this area below the dotted line and this area above it, when you tilt it clockwise like this, the area that you introduce is slightly less than the area that you get rid of, because this area is further away from the dotted line, right? But because this area that's swept upwards is closer, it's going to be smaller than the area that's further away. And if you tilt the line further, it becomes more obvious, right? That this area here that you're gaining is much less than this area that you're losing, because this area is further away and therefore is being swept more every time the line comes down. And so this area here is that's perpendicular to this mirror line here is the most optimum way of doing it, and there were two values that did that. So that's quite wishy-washy, but it's probably more thorough than you'd actually want to be in the exam. And I thought that was by far the most difficult question, so I thought I'd spend some time on it. Next couple of questions aren't too bad. You've got a function here, which I'll call f of x, and you've got a function here, which I'll call g of x, And now, if this is a factor, that means g of 1 over a is 0. Factor theorem just says, put in whatever makes this 0. So in this case, like if this was 2x minus 1, it'd be a half, wouldn't it? So 1 over a, and then that equals 0, and that's factor theorem. Now, remainder theorem says the same thing, except it equals whatever the remainder is. Being a factor essentially just means remainder 0, so you put a 0 there. Remainder 1, you put a 1 here. And of course, you've used minus b to make this whole thing 0, minus b plus b. So use minus b. And we just shove those two things in, and we get f of minus b is equal to 1, and you put minus b in. Minus b squared is the same as b squared, of course, then just swap the sign here. Same thing here, put in, I don't know why I wrote that twice, that's really dumb. Put in 1 over a, and that equals 0 when you do that. Now I'm going to times this all by a squared to get this, and rearrange it for b. Now it's asking me to solve for b, but I couldn't see an obvious way to solve for b here, so I'm going to solve for a by putting that stuff into here. Now I'm just going to be really lazy here. Squaring minus a squared is the same as squaring a plus a squared, because squaring the negative is equal to squaring the positive of the same thing. So I'm not going to mess around with the negatives there. Expand all that out, tidy it up. This is a quadratic in A, sort of. I mean, it's a fake quadratic. You can factorize this nicely into this. Jot down just 2y squared minus y minus 1 equals 0, and if you can factorize that, you can factorize this. And so it's got solutions when this is 0 or when this is 0, but this is never 0 because that's positive and that's positive, so that can go. If you rearrange that to be 2a squared equals minus 1, you'd see quickly there are no solutions there. And here, a is equal to plus or minus 1. So that means we're going to get two b values when we put in plus or minus 1. The first one, when we put in plus 1, is going to be minus 1 minus 1 squared. Notice how this is just the same. It's just 1 squared anyway, because positive and negative squared is the same thing. And the other one is going to be minus 1, which is just plus 1 minus 1, and we'll get 0. So so this one is 0, this one is minus 2, and we'll have our two options there. Quite an interesting question. This question is also interesting. It's just testing whether you're very confident and secure with your log laws and exponential laws, I guess. Bx to the power x. Just multiply the exponentials in this situation, so that's going to be b to the x squared. This I can take out into being this take away this by a log law, the subtraction law there. This is b to the power minus 1, and this is times this. Now, it's just testing. You can't do anything with these two. When you're multiplying logs, there's no easy way around it. I'm going to use power law, though, to bring down all of these powers, like this, including this minus 1. And now log b is just 1, so that just goes, though I haven't done it yet. I've just grouped the x's on this line. I've just grouped the x terms. Now I'm going to say that's 1, so it goes away. And now I'm also going to write this as this, because I thought it would be helpful. And of course, we're looking for this to have a repeated root. We need b squared minus 4ac to be 0. So this is a, is just 1. This is b, and this is c. So I want b squared, which is this, squared, minus 4 times 1 times this to be 0, to have a repeated root. And now here, I actually thought this would be better. Again, don't just think this is the power law and bring the 2 there. That doesn't work. That's only when you're squaring the inputs, not the whole log. I actually wrote this back in this form because I realized it would actually be better if I did. These negatives, by the way, cancel. And then when you expand this out, you get log squared of this minus 2 cross terms plus log squared of that, just by expanding brackets. And this is good because this is the same as this. So we just end up with plus 2 of that term, which is amazing because that factorizes back to a similar thing that we just expanded, which is really cool. And now, of course, we can square it both sides. In fact, we can use the log law where we add logs together, we multiply the inputs, then we can square it both sides. And so we have this, but of course, a to the power 0 equals bc. Well, anything to the power 0 is 1, so we need bc to be 1, which is this condition here. I thought that was quite a nice question. I think this is the last question, if I remember correctly. So this is the sine graph between 0 and 2 pi. Now, my attention was called to this one straight away, because it says you don't actually want to integrate any of these, which to me reads as you want to draw these and figure out which one is best, or which one looks the best. Now, sine to the power 100, notice how sine is always below or equal to 1. And now, when you raise a number that's between 0 and 1 to the power 100, you squash it right down. Right? Numbers between 0 and 1, when you raise them up to the powers, become smaller. Right? So this graph, when sine of 100, is really, really small, all the way up until we get close to 1. Now 1 to the power 100 is a 1, so it must kind of make its way to 1 really, really steeply here, and then crawl back down again, and then do it again. And in fact, if you put it in a computer, it looks like this. Now that's relevant because it's going to look like it's going to have quite a small area. It's going to be a positive area, but it's going to be quite a small area. So I just crossed that one out because I was like, well, that's quite small. Maybe it is actually the answer because I haven't looked at any of the others, but it's a very small number. Now, this one next, sine cubed, similar. It's going to be squashed down a little bit, but not as much. Go up to 1, come down again, and then negatives cubed to negatives, so it's going to be squashed down again and squashed down up to here again. Now the thing is, when you take away 1 from that, because its maximum is only 1 in the first place, it just gets brought down into this negative area. So it's going to come up here, down here, and then all the way down here, up here. And when you times by 108, that's still going to be down here. So, and then when you integrate something that's just below the x-axis, you're going to get a negative number. So I've said this one is a small positive answer. This one cannot be the biggest because it's a negative answer. Okay? So this one is at least bigger than this one, even though maybe I shouldn't have crossed this one out, as I said. But anyway, I was being hasty. Now this one's a similar thing. X squared minus 4 is a negative number between 0 and 2. Any input between 0 and 2, x squared minus 4 is negative. Sine to the power 8, similar to sine to the power 100, squashed down, because it's to the power 8, these negatives become positives, and so it goes back up again. And so this is always positive, this is always negative, positive minus negative makes negative, so this is a negative function. It entirely lives below the axis. And so when you integrate, this is also going to be a negative number. So I crossed out that one as well. And now, part of the reason I did cross out this one is because I had looked at this one, couldn't help but to look at it, and it looks much better. It looks much better, because cos of x looks a bit like this. These two are both below the x-axis, that's why I just said that. Cos of x is this. When you add 2, that's shifting it up. So it's going to have a peak at 3, and a peak down here at 1, from minus 1 up to 1, when you shift it up by 2. And so you're actually going to have a really nice big area here. But also you're cubing it. And we talked here about raising to power squashes the graph down, but because you've escaped the numbers 0 to 1, and you're cubing things bigger than 1, you're actually just going to be much bigger. Like 3 cubed is 27, 1 cubed is still 1, 3 cubed is 27. So you're integrating a massive, relatively speaking, function between 27 down to 1 up to 27 again. And so that's going to be quite a big area. So that's why I crossed this one out, because I had already sort of looked at this and thought, that's going to be quite big. And now one left to do, this one is winning, one left to do is this one, 3 minus sine to the x. Now, sine of x, I should say. So you take the value of 3, which is up here, and then you take away sine. Now sine is 0 at 0, so it's going to be here. And then at pi over 2, sine is 1. So at pi over 2, you're going to go down to here. So it's actually going to do this a similar thing here with this. But then it's going to go back up again, right? Because the sine of pi is 0, 3 minus 0 is 3 again. So it's going to go down to 2 and then up to 3 again. So it's going to look like this. And this is only between 0 and pi, so it's just this column we're looking at here. But you're raising that to the power 6. I don't even know what 3 to the power 6 is. It's big. 2 to the power 6, I think, is 64. This is definitely going to win. The numbers are huge. Absolutely huge, mate. And so when you integrate, you're going to get a really big area between 0 and pi. So this is definitely going to be the answer. Anyway, thank you for watching. That was quite a difficult paper, I thought. And I'll see you next time.